from words. Most of what we're going to do today is going to be on a piece of paper that you have, and then we'll transfer that over to your lab notebook just by gluing it in. So once you've added that to your table of contents, let's go ahead and take a look at the gold sheet. And if you'll take a look across the top, let me make this large enough so that you can see. If you take a look across the top, we already know what acceleration is. Acceleration is the rate of change of the velocity. We know it comes from the slope of the velocity versus time graph. And this word acceleration is one that we not only put on motion diagrams, we can calculate the slope of a velocity time graph. We can also do some simple calculations as well. Now, if you take a look at what you have in the middle, you have a data table with your time data and your velocity data. And what I want you to do is I want you to draw a quantitative VT graph using the data that's provided. So if you take a look at the time at time 0, we have a velocity of 5. At time 1, a velocity of 10. At time 2, a velocity of 15, and so on. So you can clearly see that this object goes a positive direction. And you can also see that it is speeding up. Now, I don't want a qualitative graph, I want a quantitative graph. So that means we've got to make sure that we get our numbers written on there. We know this is time 0, and I know I've got to go all the way up to a velocity of 20, so I'm just going to go by 5s, 10, 15, 20, and then I know I've got to go out for 3 seconds, so I'm just going to skip a line 1, skip a line 2, skip a line 3. You did the same thing as well. Then you just plot your data. At time 0, you're at velocity of 5. At time 1, you're at a velocity of 10. At time 2, you're at 15. And time 3, you're at 20. So it's a perfect linear relationship. Okay, so that's not new. We've seen that before. Now, the one thing we can't tell on a velocity versus time graph, we cannot tell the starting position of this object. I just know that it's moving in a positive direction and it speeds up. I also know because it's moving in a positive direction and speeding up, then that must mean I have a positive acceleration. I know it's a positive acceleration because 1, I have a positive slope on my graph. The second reason I know it's a positive acceleration is because if I'm speeding up in the positive direction, then my velocity and acceleration have to go the same direction. Now, what we want to do is we want to just do a quick calculation of what the acceleration is. I'm going to show it on the graph, although you can do the same thing on a data table as well. I'm going to take my rise and my run. In this case, my rise is not 20, but my rise is 15 meters per second. And I did forget to put my units on my graph, so let me put those on there real quick. My velocity is in meters per second, and my time is in seconds. Then I'm going to divide that by my run, and in this case, my run is 3 seconds. So my rise, 15 divided by 3 is 5. No doubt you all can do that. And then I know that my unit is meter per second, which tells me for every second, my velocity changes by 5. And we can see that on the data table as well. Every second, it's going up by 5. Now, just a quick review. We've already written an equation for the line in here, so that's not new. I just want to go through it again because we're going to use that in the next part. Now, if I write the equation for the line, I can start with y equals mx plus b. That's generic for anything that is linear, so write that down as we go. I know I fill in the m and I fill in the b, and in this case, my slope is 5. And in this case, my y-intercept is 5. Okay, so that would be math language. Now, we don't leave it as generic y's and x's. Rather, instead, we want to make it specific to the equation that we have. So we know that instead of y equals, it's vf equals, and 5, obviously. And then delta x is actually what's across the x-axis, which is time, plus 5. So that would allow me, if I wanted to solve for the final velocity, all I've got to do is put my time in, if it's something larger than what my graph has. Now, we've written this equation before, so that's not new. Let's go ahead and rewrite it here. VF equals A delta T plus VI. This equation works only if you have a constant acceleration because that's the only way you would get a linear relationship on a v versus t graph. If you haven't written that in your lab notebook, you want to make sure that you do that. Now, we can also write this exact same equation and just rearrange it a few ways, and I'll show you how I'm going to do that from the graph up above. So first of all, I know that the slope of my line was rise over run. And I know the slope of my line represents acceleration. Okay? So what I'm going to do is go back up to my graph and show you what we did to actually find the acceleration based on that graph. Essentially, what I did was I took my final velocity, which was 20 in this case, and my initial velocity, which was 5, and I subtracted those, and that's how I got 15 meters per second. So instead of saying rise, I can simply say final velocity minus initial velocity, all that over the amount of time it takes. Okay? Now, this equation is this one, simply rearranged, and you can also rewrite it as delta v over delta t. Now, if you think about final velocity minus initial velocity, the order of that absolutely matters because you know if you don't set it up the correct way, you will get a positive when you're supposed to get a negative or vice versa. So if we were using this equation right here to find acceleration, okay, then that means that all you got to do is know your final velocity, your initial velocity, divide that by your time, and you've got it. Now, if you know that acceleration is any change in velocity over change in time, okay, so acceleration is a change in velocity over change in time, then your units for acceleration could be any velocity unit over any time unit. So some possible units we've used already have been meter per second per second. We've also used centimeter per second per second. Now both of those can be rewritten as meter per second squared, that's the same thing, or you can also write it as centimeters per second squared, which some of you have already been doing. However, it doesn't always have to follow that pattern. It could also be a mile per hour per second. Okay, so that tells me for every second, how many miles per hour would that be changing? So for example, you might have that acceleration if you're dealing with the shuttle that's launching because it's going to have a really, really large acceleration. You could have a kilometer per hour per hour. Okay, once again, as long as I have a velocity unit over a time unit, it's completely okay to mix and match. I could also have a meter per second per year. Again, it is a velocity unit over a time unit. So they don't always have to match, and that's the point I want to try to make. So let me just do one quick example to show you what I'm looking for, and then you can get started on your calculations. Now, I know that in this problem, I'm going to be solving for acceleration. So that means there's a VF somewhere in the problem, there's a VI somewhere in the problem, and there's a delta T somewhere in the problem. So I've got an object. I know it's slowing down because it tells me. And it's slowing down from 30 miles per hour, so my initial velocity is 30 miles per hour. And I know that my final velocity is 10 miles per hour, 10 miles per hour. And I know all of this takes 2 seconds to do, so there's my delta T. Now, let the units help you figure out what your givens are. We want to know what the acceleration is. So once again, you got to show your work over to the side. Then you subtract VF minus VI over delta T. I write my formula. Next, I take my VF, in this case it's 10 mile per hour, minus my VI, which is 30 mile per hour. And I divide all of that by 2 seconds. Now, there's no doubt in my mind you can do the math on this. I get a negative 20 miles per hour, all that divided by 2 seconds. So your final answer is going to be a negative 10. Notice what my unit is. It's a mile per hour per second. All I did was I simply took my units that I had all along, and I just shifted those down. This is why we don't use the divide sign, right? I'm going to go ahead and use a line to show division. Now, if I were going to sketch the xt, vt, at, I know this object is going in a positive direction because my velocities are positive. I also know that this object is slowing down. So xt, AT. And if this object is slowing down and it's moving in a positive direction, then that means my acceleration has to be the opposite direction. So my AT is going to be in the negative area. Go ahead and show your work and do the calculations that are left on the sheet.